Hi, and welcome to today's live stream. My name is Danielle. I am very pleased to introduce you to our first Rye Twitch live stream with someone that's going to take us through a recent book. So today we have with us Alan Calvitti, who holds a PhD in electrical engineering and computer science from Case Western. He has been in touch with Wolfram Research for quite a while and has done some pretty interesting things. So we've asked him to join us here today to actually walk through a real-life data science experiment. This is a live coding. We've had some folks join us on our Zoom session so that we have some questions coming in. But if you're joining us here on Twitch, feel free to ask questions in chat and we will try to address them throughout the session. Alan, it's all yours. Thanks.
Thank you very much, Danielle. Very happy to be here. This is my first live coding session. So hopefully we can get a lot of the details here sorted out. This coding session is going to focus on a chapter that's going to be included in my book. This is the FICO XML challenge. This means explainable machine learning challenge that occurred in 2018. This is my entry into this challenge. And it's based on a real-world data set that's been obfuscated to some degree by FICO, which is a financial services company. Before I get into this particular chapter and we start looking at the power of the Wolfram language to perform these transformations in query, let me just give you a little bit of an overview about what my book is about, because this is going to wind up in it. So I've been working for about 10 years or so in healthcare informatics, and this is a branch that sort of combines clinical and bioinformatics like data that is real-world importance, essentially. And what we did for many, many years was, while I was based at University of California and at the Veterans Administration, is we studied how doctors interact with computers and with patients during real-world visits. And I think that that's apropos to this particular coding challenge, because we want to focus on real-world data sets. Unlike many books on data that are very episodic and just basically take each chapter, show you some particular technique or method, but then they move on with some other piece of toy data. And so, for example, here I'm showing you, this is actually a published figure that we put out in a publication last year to show you how many different channels of data went into one of the studies that we performed. So, for example, we captured all the mouse activity during the course of here you're showing just a single visit, and it's 30 minutes long. So you can see that there's information coming from the computer. There's information where later would tagged by human taggers went through the video and coded that. There's keyboard activity. There's also eye tracking, and then there's a lot of video type of data where we look at what the behaviors were of the doctors and patients. So this actually forms the backbone of the book. So the book is something like 30 chapters. I would say that maybe 20 of them are related to everything about these types of analysis tasks from the very beginning. How do you index the data? How do you even manage it? How do you create the data dictionaries? How do you analyze it, create these visualizations, and then ultimately how do you organize your results? And essentially, as I built this, and I did this over a period of many, many years, when version 10 of Mathematica came out in 2014, I knew right off the bat that this was a major leap in the power, because the sort of queries that took me 1 or 2 pages, even in Mathematica version 9, all of a sudden these new tools like associations and the query system allowed you to very much compress these down, and just it almost felt like having a whole new language on top of the one that we had before that was primarily dealing with let's say not numerics, because it always had symbolic sort of transformation stuff, but these query engine that you put on top of it really makes your job a lot easier, essentially. Okay, so just to show you, I'm going to open up one chapter from my book just to show you how complicated the data sets themselves are. So they're definitely hierarchical, and there's lots of dictionaries. There's lots of temporal data here that gets involved. There's data that is clinical in nature. There's data that's more kind of informatics and usability in nature. And we sort of had to combine all of these layers to make sense. So we published some of the results. So I knew that in 2014 that I would have enough material to do a lot. And basically, this is why this book, even though it's 30 chapters long, it's not as if I wrote it out in a year. It took definitely some amount of time to make this happen. Okay, so all this stuff is available online. It's very shareable, and I can share both the actual notebooks or the PDFs, whatever people are used to. Okay, so getting back to this particular challenge, again, I've not integrated this into the data set into my book yet, but basically this FICO challenge is one of the chapters that I call excursion chapters. So they're not directly related to this informatics stuff, healthcare informatics. So I'm gonna close this, okay? So I'm gonna show you this data set that is basically self-contained, essentially. So the data, and again, I'm not going to go through even what the major aspects of the tasks are, but essentially you're giving a fairly basic data set, which consists of, in this case, it's simply a table, a single table of data with about 10,000 rows of data that are accounts, and you're supposed to be able to predict whether the accounts are going to be defaulting on these loans called home equity loans, because this is a financial services company. And they're giving you some numerical data about each account. There's 24, basically the data set is 10,000 rows by 24 columns. And you have one label that is basically a binary label that says each account in their history was either good or bad. Of course, all this stuff is de-identified. There's no actual account information available. So this is basically it. So this is very self-contained. And the task, however, is that you cannot apply neural networks or some of these fancy machine learning techniques. The idea is that the regulators and even their internal teams and even the account owners, basically, when if somebody gets rejected from a loan application, the idea is that they can come back and bring some action against the bank. Why did I get rejected? Well, if you show somebody a neural network, well, you have all these weights and you have all these parameters that are involved. That's very difficult to explain how you came to the decision. So even though neural networks might have a very good performance, they're not easily explainable. Okay, so there are many other tools that are much more explainable. So this was the nature of the challenge. Now, I'm not going to focus here on the mathematics or the statistics. And in fact, even in my book, there's math and statistics involved, but it's in the background. Really, the point of the book is to highlight what you can do with the Wolfram language that makes your life easier as a data scientist. Okay, so for example, there's this query function or really an operator that was introduced in version 10. And this query function or operator can act on any expression in Mathematica. It doesn't have to be a data set, doesn't even have to be an association. You can query a list if you want to. And some of the major features are that the query can act on multiple levels. And of course, I'm going to show you and highlight where this happens in the actual data set here. You can compose different operators inside of the query itself. You can nest the queries inside of others. Okay, so these two major things that you can compose things, but also act on multiple levels, as if you can do like a map at multiple levels, essentially. So all these things are very difficult to do in other languages. For example, try to do this in Python, nested list comprehensions and dictionary comprehensions. You will find that the syntax is much, much more succinct, much easier to debug, much easier to write and read, and the code itself it's much shorter. My job today involves writing Python a lot. So basically, I see this firsthand, this tremendous gap in the power between languages. Okay, so basically, I'm showing you here a bunch of different nodes. So let's just dive into the task itself here. What I'm going to show you here, I'm going to put these two notebooks side by side. This is the actual submission notebook. This is essentially what I submitted for the data challenge. I didn't win it. I don't know who won it actually, but I thought this was a pretty decent job in any case. So this is going to be on the left-hand side, and on the right-hand side, I'm going to show you essentially slices of data that were not in the original notebook. Okay, so let's start here by showing you, after I show you the main data, I'm going to show you what I actually came up with so that you're not left hanging with what is the point of all this. So I'm going to show you what I came up with as the main deliverable for this particular challenge. So the challenge is to predict who's going to be who deserves a loan and who doesn't based on their numerical the columns of the variables, essentially. Okay, and what I came up with in terms of explainability is that if you treat each one of the columns independently, you should be able to build a classifier for each one of the columns. I'm sorry that my screen jumps around a little bit. This is simply because I have Zoom running and other things going on. Okay, but this is basically, now you're looking at what the essentially the deliverable is from this data set. What I'm showing here is a set of accounts. Oops, I think my mouse is kind of stuck here. And then what I'm showing here are codes that represents the columns that I showed you earlier. They're slightly encoded, so you're not seeing the full names of the column. If you look on the right-hand side, let me try to fuse this here real quick. On the right-hand side, you have these column names that are actually given by the challenge, and they have the full names. I essentially shortened them. I did camel case shortening. So I substituted these names. So for example, ERE simply means external risk estimate. MDE means month or since oldest trade open and so forth. Okay, so these are just shorts. And what it is essentially saying that for these particular account, when you look at the classifier that I built, and I'll show you, and that's the bulk really of the approach, is how do you build the classifiers. But basically, each of these are treated as a separate classifier. So that then for each of the accounts, I can say whether this particular classifier would classify this account as good or bad in terms of the risk performance. Okay, so for this particular account number, A0001, you have 9 independent codes, essentially, or what really variables that predict that you're going to be a bad account, and only one of them that predicts that is going to be a good account. This table is called a reason table or a reason code table, essentially, because you can inspect this directly. You can basically say, if you're the account holder or if you're the regulator, you can hover on any given account or group of accounts and basically ask the question of, which of these numbers really are separating this account from the bulk of the good and bad performers, essentially. Okay, so now that I've shown you the end, let's go back to the beginning here and show how the data is organized here. Okay, so each one of my projects essentially starts in a very similar way. I have a set of associations in which I put in metadata in terms of, I have a folder. In this case, it's a Google Drive folder, but I'm going to show you how I even get some of this data from the Wolfram data repository. But basically, you can structure, and of course, you can inspect it. So, for example, if I were to look at the meta directory here, so you have a set of, this is an association, right? So you have a base directory, you have a set of data directory, intermediate, and so on. And you can grow this over time. So it's very flexible because you can add to it as you go along. Okay, so now I've indexed this data already. So now I'm going to show you this index. So now the index, this is a hierarchical data set, and I use the function that I created, which is in the appendix of my book, called file names map. And I can show you a little bit of detail about that if we have time. But basically, this mirrors the entire file system. This is similar to Python walk, and many languages have this. But this is a one-liner function that is recursive in nature, and essentially you can point it at a basic directory. In this case, it's the meta data directory, and now you have a nested dictionary where you have not yet imported the data, but each one of the keys that you want to deal with is actually pointing at a particular file system. I'm sorry, at a particular file that you can then import. And in this particular case, I only care about CSV files and Google Sheets and Wolfram MX format files. Okay, so here's the data dictionary, for example. The data dictionary is actually a set of dictionaries. So when I drill down on the HELOC dictionary called the main dictionary, you see that it's another table. And for example, here's how I do the mapping of the short names. I have a basic description. I get a monotonicity code, which is important for saying whether it's going to be going up or down, whether the higher number means good or bad, and so on. Okay, so essentially every project that you deal with in data science, you're going to need some of these kind of resources that do data dictionaries. All right, so the first part I want to show you is called data prep, essentially. This is all the data wrangling that you do before you get into the analysis proper. Okay, this is actually a very large chunk of your day-to-day job if you're a data scientist. Even if you do machine learning, there's simply no machine automation tools that can do these basic, because every data set and every task is so different that essentially you're starting from scratch in terms of how you normalize the data, how do you group them, and so on, before you start in your statistics. For example, here, I start off with the dictionary that you saw before, and then the first thing that I do is group by role. Let's see if I have the role here. The role here is basically just saying, is this the target variable or the predictor? So that's the first thing that I'm essentially going to do is I'm going to group by these two. And then I'm going to down the predictor branch. And then I'm going to select the descriptor for each one of these. So let's just break this down, for example. If I were to take this is very simple, right? Because this is just a dictionary here. So group by is one of your best friends as a data scientist. It's one of the most often used functions. I hardly ever use select. I pretty much use always group by, because what it does is it allows you to scale up the data and do multiple branches at once. meaning that in Mathematica, so you can actually do things like this. You can say like, well, now that I've grouped them, I can go down the all branch, and I'm going to do like framed, for example. Let's see if this works. Okay, you can see that here I framed, and by the way, you can only do this in a symbolic language that you can kind of wrap around this kind of, just to test where I'm applying the different levels. I'm applying this query frame, essentially, down at the level, and notice that I'm doing this at all the different branches. Okay, so there, when you group by role, you essentially create these two branches called target and predictor, and all these are essentially nested underneath that. Now, if I were to frame at each individual level, because each one of these is its own association, then you would see that the frame is actually applicable, and this is transparent on the individual associations, so it actually goes down to the value here. This is extremely powerful when you're testing things. When you're, when you're exploring the data, when you're exploring the levels, often the data doesn't come with a schema. Unlike SQL, this is why they call it the NoSQL world. You don't have a schema, so all day long you have to do these kinds of things. Here you can see that basically I'm applying it to this level over here. But the fact that you can do all here is one of the most powerful aspects of the Wolfram language. Again, I don't know that Python, I'm still looking for a way to do this, essentially. The way that they have to combine lists and dictionaries is just a mess to have to deal with. But here you get this very clean, very nice, coherent, and very orthogonal system in which you can kind of perform these queries. So if you were to like select role rather than by group by, you would have to say select target and then do something at target, and then select predictor and do something at the predictor. But here by doing group by and then doing this, you're actually doing both branches at the same time. So I hope that that's, that if you learn nothing else today, that's actually one of the main things that I think is a very powerful aspect of the language. Okay, so here I imported, I'm showing you how I would have imported the data for the actual challenge. So I imported it from my, from Google Cloud. But here I'm actually importing it from the Wolfram data repository. And basically all you're doing is essentially just pointed to the actual research object, okay? And then I had to do a little bit of cleaning here. I wanted to get rid of the quantities that were inserted there. But so essentially now this is my raw data. Now notice that I have this data, and then data itself is actually a dictionary. Now I'm creating a new key, and I can query this. I'm basically going to say, like, let's say if I say HELOC data keys, and you can see how many different branches I've added. Now, obviously, a lot of the stuff is in memory already. When you start from scratch, you would only have like raw data, and then you would add these things as you go along. But this allows you to essentially stage your data sets as you're processing them. And this is analogous to Git commit messages, right? So if you have like Git commits -m, and then you have like a message, like raw data added. This is essentially something similar to that. It's a little bit more simplistic. There's no like actual version control going on. But basically, I'm going to show you how all of these keys are essentially doing that. So this is the raw data as you start off. So what are we going to do next? The first thing I'm going to do is, you notice that this is a raw table. There's no actual, there's no keys by account number. And in fact, no account numbers were given. So the first thing I did was create, I added account numbers, and this is how I did it. So I use this function called association index, which is in my appendix. And this is, again, most of my functions are very simple one-liner operators. And this is what it does. If you have this as an input, when you apply association index to it, you get back a new association that is actually keyed by the numbers 1, 2, 3, and so on, okay? Now, once you do that, that's the first thing that I do. That's the first step in the query. You notice that this entire thing is a query, right? So in other words, HELOC data, raw data is the input, and now everything that I've highlighted is actually this query that I'm going to use to create this output called account data numbers. So this step does this. It adds these numbers, just the numbers themselves. But then what I'm going to do is I'm going to process them. And what I'm going to do is essentially say, take these numbers, convert them to strings, and then remember, this is something that many people are not familiar, even if they're familiar with the Wolfram language. This means compose, right? So you're basically saying, go to the key map, and these are the keys, right? 1, 2, etc. These are the keys here. Go to the key and map the following query. So I'm going to go and I'm going to map this. So this is a subquery. And so what I'm going to do is essentially say, turn these into strings. That's this. And then after they get converted into strings, use this particular function called string prepend to. And again, this is my function. and it basically does this. So for example, if you have this list and I apply this string prepend to up to 5 characters, you're applying basically just zipping it with zeros, padding it with zeros essentially, okay? Right? So now I appended, I prepended 0, the character 0, and then I'm gonna prepend the letter A for account. And this is what happens after you're actually done with that. So you start off with this. So you can see that it's all very readable, right? It's almost like writing in English. You're writing from left to right. You're not carrying, when you do these operator forms, you're not carrying with you all the baggage of the input data itself. If you were to write these as functions, you would always have to carry the parameter, which is actually the input at each stage. But here, because these are composed together, this entire operation is actually being performed as a head, as an operator on the input. So it makes it a lot cleaner to write and read, essentially. Okay, this is a major advantage. Many languages are trying to replicate this. In Python, I see that users are want to do this, but very, very difficult to do. Pandas, which is a Python kind of library, does like a tiny, tiny little bit of this, but it cannot do all the generality that you can do here. Okay, but this is the one you can see throughout that I use this technique all over the place, basically. Okay?
And
All
before
right, so
you move on, Alan, you do have a couple questions in chat. Not sure the best way to get those to you other than just say, hey, you have some questions in chat, and make sure you can see them.
Okay, so do you want me to read them out? I can see them here.
That would be great.
Okay, so a couple of the things are related to my book. Yeah, my book is not published yet. We're scoping for this this summer. Just asked for an extension actually because I have a new job. So the title is going to be Functional Data Flow. Let's see. So they encounter issues with large data sets. You know, I don't. You know, this depends a lot on your resources. The more resources you have, and maybe it's the style that I write. I find that I don't have a lot of issues with the kernel quitting. Sometimes data sets has some bugs, but basically, you know, I worked with a startup where we did work in the cloud, and we were dealing with something like 50 gig data sets, something like that, 30 to 50 gig. But we, you know, from Amazon, basically, we rented out 300 gigabytes of memory or more. And so we never really had any issues with Mathematica Online, and that was, I think, Web Mathematica. So as long as you have enough resources and you know, kind of, and you don't commit errors on your part, on your end, I think actually Mathematica is pretty stable. It gets a really bad rap. Now you have to kind of be aware of its limitations. Sometimes there are some bugs, of course, you know, but they tend to be pretty well localized. So yeah, so that's you know, I would love to get into a discussion about dealing with very large data sets, but I don't think that this is the place right now. But I would say that I don't have a lot of problems with kernel quitting. Yep. And Gustavo asked, I found that list of associations are faster than data sets and query work just well. Yeah, okay, so this is actually the worth pointing out is that data sets, like I mentioned before, you don't have to query data sets. It gives you this, you can see that since this is a data set, then syntactically you can just do this. You can just do this, right? But I can actually just write this as follows here. I'm gonna say this, if I normalize this, and I'm not gonna show you the normalized version, but basically this takes it from a association. Let's see if I can do just one. I'm going to take the first few rows. Just to do query. Okay, all right. So I'm gonna take just the first few rows. Now you can see that this is basically a list of associations, right? It's 3 rows of the association. I can take this query here and just create a new query, as long as you wrap it in the keyword query, right? And it should work the same way, essentially here. Okay, you see that now? It basically what I did was I added the account numbers here. So you don't actually need data sets. Data sets, however, allow you to basically chain things together very nicely. And of course, it also gives you the formatting. As far as I know, most of the issue with data sets is basically it's a front-end formatter, so that you can get these very nice sort of not only tables, but you can do, and I'll show you later, how you can do sort of maybe I can show you here a couple of these things. Yeah, okay, here's an example where you can see like a nested, this is a data set doing a lot of work for you, right? Pandas is something similar in Python, but it's not, I don't think it's quite as good. You can go like almost like 8 levels deep. This is basically a data set where you have risk performance, and then these are nested under predictors. And you can see that, you know, it's actually quite a lot of work if you were to do this manually. So, you know, if you were to cloud deploy this is essentially like better than a spreadsheet, right? Because spreadsheets, it's very difficult to like nest this data. So this allows you to do a lot of like this kind of like nesting of headers and so on for you. So you should think of data sets as sort of being just a wrapper, but the queries themselves don't need to be conducted on data sets. And I think that I think Gustavo's right that there are some issues still with dataset itself because of its type system that it slows certain things down. So if you're given a choice, normalize things, and then you're working with lists and associations, and then do the queries there, and then you can always wrap a data set at the end. Okay, remember I took the first 3 rows only, right? So you can, and in fact, I do this trick sometimes when I run into problems. I normalize, I do some stuff, and then wrap it back into data set. And you can do this. Okay. All right, just to move along, I think that what I really wanted to do is introduce some of these functions, just kind of like string prepend to. I'm really proud of the appendix in my book, which is really these functions that I realized I started using over and over. That basically I accrued during the course of real work, and now there's maybe like 100 of these operators, and some of them are obviously more useful than others. Some you should definitely, I think, it should wind up in the language. I hope, key group by, for instance, or the nested version of merge, or even like the key value version of outer product. These are things that are so natural that I use them over and over in data science. So I think hopefully they'll wind up in there somehow. Okay, so just to move on, again, I don't want to spend too much time on the specifics here, but really just to give you an idea of the flow is that, so let's see here. So we did we added the account numbers, we segregated multi-ordinal variables. I think that what I did, so let's see how we did this. I don't want to get too much into explaining this because this is a very specific function that I had to write. But basically it says that if a function has a value of 8 or 9, give it a new column. And try that by hand. Take a function that basically goes down each one of these things, and if the value is like a 7, move that into like a new column, and I think I called it, so for example, this thing like other, right? So if this particular column has these particular values, move that and create this thing into other. And so for example here, I'm going to show you how basically by inspecting that particular column and then grouping by the head, you can see that most of pretty much 99% of these values are actually not 8 or 9, but there's a few that are like 8 or 9. If this one happens to be 9, but basically you can see that pattern matching works very, very well here, right? So basically you can have very complicated patterns here, and as long as you can kind of identify the pattern, here in this particular case, I'm looking for negative values, and I can sort of do, replace them to missing, but here you're actually moving them to a completely separate column, okay? So I want to stress that these functions are, sometimes they're head scratchers. It might take you like an hour or a day to write something like this, but once you have it, you tend to use it over and over. It's a very kind of like classic thing. So if you do nothing else with my book, like really go down to the appendix and start using these functions, because I think they're extremely like useful. I found that I've used them, in pretty much like most of the projects that I've had since the original ones in which they were conceived. Okay, so we do more stuff over here. We add missing value, tally. Notice that I do a lot of group by, and you can ask whether something is missing or not. Once you create something here, let me just do this like this. Let's do something here. Let's see if I can do it something like this. If I go down to like one account number. Yeah, so basically it appended these 2 sets of things, and basically it's saying which one of these are actually like missing. So you notice that the branch called true, by the way, I have to say that unlike Python and many other languages, the implementation of associations in the Wolfram language is very cutting edge. It doesn't rely on hash tables. It relies on what are called trees, and that allows you to have symbolic expressions for the keys. If you're familiar with JSON, like in JSON, like the keys can only be strings, basically, right? And in Python also, they have to be immutable variables. You can only be like certain things. But here you can essentially have arbitrary things in the keys. That makes it a lot more convenient to do things. You can have dates, you can have range of dates, and so on. Here in this particular case, I basically said group by missing Q, and then a pattern like this basically says go down the key name true, compute the length, and then just call that a new column. All right. So essentially, once you do all that, you will see that there's a new variable here called Let's see if I'll just go down one account here. Okay, so basically this particular account number has two columns that are missing, this one and this one. And here you can see that this particular query essentially computes the length by going down the ones that are missing, and then just assigning it this new name called missing variables count. Okay, how much more readable do you want it to be than this? I mean, this to me is something that you can come back to like 3 months from now, 6 months from now, and really, it's just as readable as when you wrote it. As opposed to when I was working with version 9 of Wolfram language, this would have been a lot more complicated. It would have been like maybe like a paragraph long, and then 3 months later, 6 months later, when you revisit this kind of query, you probably would have started from scratch because it just takes such a long time to read and try to inspect the entire thing. Okay, so having these very short query patterns means a lot. And also, the other thing is, you don't really want to name this, and you don't want to call this a function by itself, because there are too many variations and combinatorics in what happens in the middle. Okay, so there's this concept of use patterns rather than functions. Of course, we define functions. Of course, we define operators. But when you have something like this, it's just like in Unix pipes, right? The combinations of different things that you can do is so much bigger than if you were to name this particular thing as a given function. So keep that in mind. Okay, so now you do these basic standard things such as rescale the predictors. So let's see if I have an example of that. Let's go down here. Scale, so rescale the predictors. You can see that I'm basically just going down and scaling this from 0 to 1, no big deal. So let's see, I do by group by risk performance. Okay, now here's something that I want to show, and maybe this is because we're running out of time and I want to save some time for question. Here's something I want to show you how to combine different queries. Okay, so here's a stage of the data called rescale predictors. Okay, and you see that essentially they're sort of like ready to go in terms of now every one of these predictors lies in the same range. You can do statistics with them. Now I'm going to essentially show, what are the basic, let's visualize the statistical distributions between the good accounts and the bad accounts by the columns. Okay, now I created this branch called predictor order statistics. Now this is numerical. And you can see what this does. Essentially, I have a function that, how did I create this? Well, I started with this particular set of data, and then I grouped by the good and bad accounts, first of all, and then essentially took out the account numbers, got rid of them. Merge is a very, very powerful construct because you can pass functions in it, okay? If you come from the SQL world, you're probably more used to joins, and there is an operator called join across, which does what join does. But you cannot pass specific functions to join, but you can to merge. So as you're merging, you can essentially post-process after you merge by the particular, the account. So basically, once you get rid of all the account numbers, you take all the good accounts and all the bad accounts, throwing them together, and then I'm applying this function called median IQR, which is essentially one of my functions that simply computes the median and interquartile range, okay? And that's what you get here. So at this particular stage, you only have for each one of the columns, the tally, basically, the median and IQR, and then I have another function called give me the graphics version of that creates this particular view. So you have the median and the interquartile range. But then I thought, this morning, what if you wanted to show the entire distribution, like the histogram, not just this? How would you do that? Well, look at the pattern. The pattern is essentially the same. Rather than, you're still computing with the same data. So let me just take this apart. And this is probably the last thing that I'm going to do here. When you group by risk performance and do group by values, like I mentioned, you're basically getting rid of the account numbers. Okay. So you essentially have 5,400 bad accounts and you have a similar number of good accounts, right? Now, by merging, I could merge and just simply do this. If I merge and did nothing but, for example, merge identity, this might take a little bit of time. Okay, you can see that the 5,400 that were in the bad group all got put together in a single list. And this is maybe perhaps another limitation of the data set format, that it doesn't really kind of auto-expand this. But if I essentially go down to out 135 and look at maybe bad, and then look at Let's look at the first two rows. Actually, let's just look at the first one. Now you should see a list of, oops, sorry about that. Let me think about that essentially, but let me see. I wanted to do one. Is it really just bad? I thought I had numerical data here. And this is some of the slowness with the, no, this is maybe just bad. So potentially I'm just like counting these essentially. Okay. I thought I'd have numerical data in here, but that's okay. So we're just essentially like counting the number of like goods and bads, I suppose. Okay, so once you have this, what I wanted to really show here, let me get back on track here, is once you have these particular the numerical information, you can go directly to the graphics. But how would you do the histogram? Well, it's basically the same pattern, because essentially you can look at this query. It's merge, delete, missing. I'm actually showing you both here because the end goal was to, how can I combine this view and the histogram? So the language allows you, as I pointed out earlier on, this query pattern is basically doing this. It's taking this query and it's actually composing two queries. It's actually giving you a list, right? This format is essentially query. When you have this, you're essentially creating a list of the two queries from the same input data. So you started off with a particular data, and now you're performing two pieces of queries at the same time. Here I'm just showing you one. It was basically delete missing and compute the median IQR. So that's over here. Then I also folded in the graphics aspect of it. So basically, it's taking the median IQR, meaning get the numerical version of that, and then apply the actual graphics call on it. So that's the G part of this query. But then the F is what I just added, which is the actual histogram, right? So the histograms themselves is a separate query, but it follows exactly the same pattern. You still have to do the group by risk performance. You still have to get rid of the account numbers. You're still doing the merge. And then you post-process both, right? So now you have join, and now you have F and G, and now you do a sort of join. Here in this particular case, the join is basically just show. There is a bug here that I just found out, unfortunately. You can see that there's a bar there, but it's under. And I don't know of a way, I've even switched them around, but I don't know of a way to actually make it visible. But you can see that they're there, because when you look at it, this one goes from 0.5 almost to center around there, and this one is slightly higher. So you can see that the bars are actually there, but somehow like the vertical pieces of it are hidden away. So, okay, so there's a bug in there, but you see the point is that you basically are kind of growing this query. If I took this out, you would get the original thing that we started off with. Essentially, you would take out the histogram part of it, and you would take out the show. Show just combines the different graphics, and everything else around it is essentially staying the same. So that makes it a very clever and sort of modular way to sort of increase the query. And very often you basically do this, and then you get back to your team, and the team says, hey, that's great, but I really want to see the actual empirical distribution on top of it. And you're not writing this from scratch, I think is the main point. You can kind of just add to it, and it's short enough that you can kind of like get the point as you go across. Okay. Right, so let's see here. So I think that was maybe like the last thing. Clearly, we don't have a lot of time left. Let me just take like 2 minutes before we open up to more questions here. But essentially, everything that I've shown so far is simply data prep. Okay, you do all these stages of data prep, or exploratory analysis in a sense, to understand how to group these different things before you get into the main classifiers or any of the kind of like statistical stuff here. So if do I have any more data here? Predictors by monotonicity code. Okay, so here's another example. So remember how there's this, some of the variables, the higher the number, the riskier the accounts, and for other columns, it's the opposite. And they were encoded in the dictionary by whether they were increasing or decreasing. So there's the monotonicity code, which is essentially either inc or dec. And basically here, I'm showing you a query. This query, I'm not going to run this query. This took 40 seconds to run. But basically, you're saying essentially group the dictionary by the monotonicity code, and then insert that into the predictors. And this is what you come up with. So basically, for each one of the accounts, the risk performance is determined. But now you're grouping each one of the predictors into the ones where the numbers, I think the lower the number, the less risky, and the ones that are the lower the number, the more risky. Okay, so these are opposite of each other. And of course, if you don't do this, your analysis is basically worthless. You're combining two things that are diametrically opposite of each other. You have to do these sort of like data prep stages. Okay, so even though they're sort of like kind of like hindrances to the smooth going, and again, you can see that all these queries are essentially just one-liners. So they're not so bad to actually like put together. So once you have these, then you have to polarize them, meaning that you flip the ones that are, which one do I polarize? The ones that are increasing, I flip them. And you flip them basically just simply by using this replace function here, very easy to do. And here's an example. You have these predictors, and now I just sort of taken the input, and this is what happens when you flip them. You can see that this one started off at 0.15, goes into 0.84. The other branch is untouched, right? Because this query is only acting on the predictor branch. So let me just show you another function that I created called query at. Query at function looks like this. And it takes advantage of fold. The reason is, and I think that this is another gap in the language, but luckily it's a one-liner gap. If you don't have query add, you have to write this. So remember that there's that syntax called where this is not a list. You're essentially saying go to one key and do F, right? But if this is nested, and it is here, you have to do this multiple times. So actually, you have to wind up doing this pattern, which is query F. And then if F itself is a data set or an association, you have to say like query, and now I want to do something, another key. So key to do G, right? And in fact, in this case, I have to do all. And this is basically what's happening here, right? So this query at essentially just enables you to list these out as a sequence. Go down predictors, go down inc, and go down all, and then do this replace, but do it in place, right? Whereas if this was just a query rather than query at, it would essentially extract this data. It would not do it in place. All right. So again, this took like a day or something to come up with. I saw that I was doing this over and over and over again. Even at 8 levels deep, you get tired of writing all this, right? So I just want to really point out that the language allows you to sort of think of these kinds of things as puzzles almost, right? When you have this, when this is your answer, it's almost like you're doing some very cool sort of mental sort of like juggling rather than it feeling like work a lot of times. You go out to lunch or you go out for a jog and you go, how do I convert this into this? And when it's on one-liner or 1 or 2 or 3 lines, it just feels like it's just very productive way of doing it, especially when you get to use it over and over. Okay, I think I'm going to stop here because we only have like 50 minutes left. As you can see, that this is only like 1/3 of the notebook itself. Ideally, we can come back and do the rest of it. After this, essentially, there's the actual work of once this is all prepped. There's you come up with these empirical distributions and you come up with the classifiers. There's a lot of actual statistical work that is involved here. But in terms of the mechanics of how you compose these queries, hopefully I gave a pretty general idea of the kind of like fanciness that goes into the language. And I think, and again, like I want to say that now that I'm using Python a lot for work, Python is not that much faster, really. In fact, for some things, it doesn't feel faster at all. And you have to think of the fact that you cannot do most of this stuff with Python. For example, look at this. This is actually an association, right? And it's an association where the values are graphics. You can do this in Python only by adding these extra packages like pandas, and even there, it's a completely new system. It's not orthogonal. It's not really integrated into the language. And if I wanted to, I can take these MDEs and create sort of abstract expressions out of them. They don't have to be strings. So basically, you cannot do this fancy stuff. This is essentially, I've published graphics that are essentially, I left them inside the associations because they look good, they do their job, right? You have keys, you got the graphics. You don't have to subsequently post-process it. This is a tremendous advantage when you're doing lots of exploratory type of stuff. I really want to stress that aspect of it, that you cannot do this at all very easily in most languages. In fact, any languages that I know of. Okay, yeah, so I think I'm going to stop here, but because we can keep going for another like 2 hours if need be. So I'd like to basically ask for any questions or any kind of like review type of stuff or general things. Let's see here.
I was about to say, some of your questions are piling up in the chat if you want to scroll back just a little bit.
All right, so let's see here. So I think this is the top, all right? So Gustavo. What is HELOC? HELOC is simply, it means home equity line of credit is simply, I name my projects. You notice that I don't use packages. Basically, I evaluate the notebook in place. If I can go back to the top here. Instead of importing, instead of saving the packages, I essentially like import, and I just do a notebook evaluation. And this is the notebook that contains all my one-liner operators. Now, so instead of having this namespace control, essentially, whenever I start a new project, I give it a name, and then I have this sort of boilerplate sets of things. You know, there's metadata, there's going to be data, there's going to be dictionaries, results, figures. Pretty much this happens in every project. So then from there on, you essentially have this as the head. So the name of the project is HELOC in this case, right? If I were to open a different notebook, and if you look at my book, the project is called Quick. So Quick will be the name, will be the head, and everything will be controlled under the head. So you can think of it as namespace control. So it's not part of the language. Okay, Carl. So let's see here. Key group by, definitely a function I would like. Okay, good, because that's I almost isolated that as being the most needed function, I think, in the language. I've said this over and over because that allows you to do nested associations very easily, right? Carl wants to do his own live coding sessions. Yeah, I mean, even like a team-based coding session would be very cool, I think. Okay, Diego asks, are you planning to place the functions in the package repository? Sure, yeah, we can do that. I think that we can do that. I'd have to know a little bit more about how I can integrate it. Right now, it's available. I can share it. It's a shareable notebook, basically what I just showed you at the top of here. So anybody can actually just get it. It's a notebook, so it's very easy to kind of do it. But it's going to be released with the book, and sure, why not? Why not release it with the functional repository? So we can do that. All right. So point out the online chapter the live stream is based on. Okay, we're going to Carl, the live coding section. What symbol is immediate after the show? Oh, I think he's asking. I think I know what he's asking. I think I pointed out in the Wolfram community that I have a function called, I think he means this, okay? So this is actually very important. This bullet operator, this allows you to do query by position coding it. Here's the definition, actually. Here, let me show you. This is my favorite invention. I have to say this. The function is essentially this. And actually, I want to thank, so people at Wolfram helped me out with this. And in particular, the people in the language, I think it's called incremental language development, where basically I had let's see if I have it here. Oh, I have to scroll all the way up here. Yeah, so this is essentially this function. Now it looks like a bullet point, and it is. You just basically just say option 8, but you can see that I'm using up values to define this. And you can see that it's position coded. Basically, for any for any function that you want this to act on in query, you essentially are saying, if I want a string split to act on the first parameter, I'm essentially querying this. And it's querying by determining how much of the function, what part of the sequence of arguments the function takes comes before the bullet and how much comes after the bullet. And essentially, I'm creating a query, a parameterized query function, where the bullet basically comes out of that. So you can see that I'm joining basically just the pre and the post aspect of it. So that then the queried function acts on the input. So basically the bullet point means this is everything on the input. Okay, so you can put it at first place, you can put it at second place. You can only put it in one place, but it essentially allows you, otherwise you would have to do something like this. You can use the function, let's see here. You would have to use essentially this. And you cannot use it past the composition point. So, and then you have to wrap it in parentheses because of the rules of commutativity and so on. So you have to do all this, and it's much less readable, essentially. Okay. So, but basically, this is what the query syntax is doing. This is really one of my favorite things. I use it all the time, and it just streamlines. Again, you save about 3 characters, and they're kind of nasty characters that you don't want to look at. Okay. So let's see. So Gustavo asks, I think MapAd accepts a nested spec. Yeah, it's true. MapAd is actually very similar to QueryAd, but I don't know that you can actually sequence the multiple things. You notice that I basically said QueryAd, FGH, or actually it's the names of the keys, right? So I say QueryAd, and then at each one of the slots, I can actually put in a query Whereas MapAdd, I believe, I'm pretty sure that the limitation, and you can actually just give the name of the keys. I can actually have queries. So for example, if a key happens to be a list, I can actually just say, well, apply this on the first level of the list, or you can do pattern matching on the list. So they're very similar, but I remember looking at that and thinking that actually it generalized it to some degree. But in many, Mathematica allows you to do many things in similar ways. So I wouldn't be surprised if in the future, we can do like MapAdd, use it rather than query add. But try applying it a query rather than a key and see if that works. All right, what background information was most useful in developing this? For somebody looking to jump into their own data science project. Okay, so there's two parts of data science, really. It's a STEM field, meaning that you have to combine multiple disciplines, primarily computer science and mathematics. And I would say that you can learn computer science maybe like in 6 months, at least the basics, enough to write interesting things, but not the math. Because if somebody asks you, this neural network has tensors and their vector spaces and whatnot, I mean, can you really teach what a vector space is and how these things behave in 6 months or not? I mean, this is why mathematics sort of like builds up on many, many years of work, and statistics is its own field, probability theory is its own field, graph theory is its own field. All those things kind of come into play. Not to say that you cannot learn them easily, but it takes a while to sort of to find the issues and the problems. So I would say, on the one hand, from the computer science point of view, I think the major gap in education is people don't understand functional languages. So even if people who know the Wolfram language, for example, sometimes they'll code, not everybody, but some people will code it as if it's like Fortran to some degree. And I'm like, no, don't do that. It's not an object-oriented language. You don't have to go that. So but basically, the way that high schools and college and university level computer science is taught, they're typically taught with object-oriented languages like Java or Python. And that's one way of thinking. But functional languages, and object-oriented languages are very useful for certain things, like when you have state, when you have inheritance, when you're writing apps and widgets and so on. State is extremely important, so object-oriented languages are very good for that. But when you're writing data flow, and everything that I've shown you here is about data flow, meaning that these states, these git commit looking states, they're basically transient states. So you can see that the data kind of floats from one stage to the next. It kind of goes in one direction only, right? So they're transient states. So that's really the meaning of data flow, is that you're essentially not updating the state that you had before. You're creating a new state or changing it. And therefore, I would say from computer science point of view, learn functional approach if you want to do data science. I think that helps out a lot, and it helps you create these nice pipeline queries. And for mathematics, learn as much math as you can. From linear algebra, graph theory, statistics, probability theory, all those things are extremely important, and I don't think you can really avoid them. You want to understand how a neural network works. Good luck if you don't know. If you're not at calculus and vector calculus and these sorts of things and linear algebra, it's going to be very difficult to find your way around it. Okay, so thank you, Diego, for liking this. Thank you very much, Carl. Okay, I'll say so. 2-hour basic overview of capabilities area. Yeah, I mean, I would love to do subsequent. This is Bruce asking about subsequent. Hopefully we can do, because I've been asked by Bruce and others if they can get personalized tutorials in some of this. And I think that, of course, I'd be happy to do personalized tutorials. But I think that a lot of this stuff can be captured pretty simply, not in a 1-hour segment, but if we had multiple hours to explain some of these concepts. People get hung up on very basic gaps, such as how do you import the data and convert it from a Excel spreadsheet into nested associations or whatever, or into a table. And those things can be explained, and they're literally, sometimes they're one-liners. How do you do like association thread or these kinds of things? So I think in a very short amount of time, you can learn the basics of being able to manipulate this data, and then get to the things that you really want to do statistically and so on. Thank you, Mitch, for also attending. Oh, thank you very much. I really appreciate it. Obviously, we didn't get to finish or even get to the heart of the matter here with this notebook. So I hope they get invited back to do another live coding. I would really love to do that.
I was waiting to see if there's anything else typed. There is one question that I don't think you addressed entirely that might make a good closing, which is what background information was the most useful in developing this? And what would be most helpful for someone looking to jump into their own data science project from the get-go? So any parting advice for newly budding data scientists?
Yeah, well, the question is, do you want to learn by doing from a real world project, or do you want to learn sort of like the steps to get you to become a data scientist? Because if you want to do the former, that's how I learned essentially. I'm an engineer by background, but the things that I had to learn in medical informatics was that you have to collaborate with a big team and learn the domain expertise. You have to understand. Basically what I had was the programming skills and I had the math, but I didn't know anything about medical informatics at all. That's the stuff that you have to like learn, right? So you pick a domain that you really like, and maybe find like a collaborator. Challenges that exist all over the place. Kaggle and other places have tons of different challenges where you can compete. This is an example of one where I entered. Not so much, it wasn't really about the prize money. It was about really, I can show people that you can do this kind of stuff in the Wolfram language. If you try to do this in another language, it would take you a lot longer. Many more lines of code, I'm sure of it. Try this in a different language and see how far you can get. So I would say that start with like a real world project, maybe like a simple one. But I would suggest Kaggle, and there's many others. If you want to shoot me an email, I can send you a list of these things pop up all over the place, and they're all kind of here's the data, here's what we want you to do, develop some classifier or regressor or something like that. I think that would be probably like the easiest way to do that. Right, rather than kind of like made up data sets or kind of the things that you see at universities often are kind of really academic, where they cleaned everything up for you and so on. It's not that useful. You don't really get to see the issues. I don't think.
No, that's fair. Thank you very much for that. And the final question that got typed in as you were talking is, what are some resources for the statistical analysis piece that we didn't get to? And I'm going to take that opportunity to formally invite you back to do a part 2 of this, where maybe you can actually get to the statistical analysis piece, but I wasn't sure if you wanted to give someone some light reading before then.
Yeah, no, thank you very much, Isaac. That's a good question. And obviously the statistics is a wide open field. You can see that we're living in the age of machine learning, where every like 10 years or 15 years, there's a completely different thing that comes along. If you'd asked me this question like 10 years ago, the answer would have been, hey, let's use, let's say, support vector machines, for example, which are tools that were widely used in biomedical informatics. Now everybody's about the neural networks. Bayesian networks is another field that I think is going to come up in the future. Those are the kind of like major thing. This particular challenge was very simplistic in the sense we just use a sort of like ROC curve. I haven't really shown them here, but I use essentially ROC curves to create a simple independent classifiers for each one of the columns. So I didn't combine them. I didn't vectorize them. I did some data reduction and so on. But yeah, hopefully, thank you, Danielle. I'd be happy to do a part 2, and then we can get into some of the statistical issues. But here in this particular project, is not very sophisticated at all. Maybe somebody can go take this same data set and try something even bigger and better with, there's an endless array of, I can suggest books for you where you can get started with machine learning and some of the techniques behind it. But the major categories now that people are looking at are, like, let's say what I call like distributed approaches, like neural networks, Bayesian networks, Bayesian approaches, statistics. Everything is statistical in nature, because as soon as you do an ROC curve, that's statistics, right? But in this particular case, the classifiers are very, very simple. And I'm not doing, besides some exploratory sort of dimensionality reduction in linear algebra, I'm not doing anything fancy here. So, but in other chapters and in other projects that I've done, of course, you can get extremely fancy with some of these things. Yeah, so let me just conclude by saying that in part 2, I'll show you that some of the distributions that I'm using are actually built into the language. So you can have these empirical distributions that are actual objects in the Wolfram language, and then they're inside of the data set. So you can organize them and essentially combine them and query them. And we use that also with Mitch in the startup that we worked at. So they're extremely powerful like statistical features in the language. Here I'm just scratching the surface, literally.
Great. Well, we are only 2 minutes over. Thank you so much for taking the time to do this. And thanks for everyone that's listening for asking your questions. And we will get some information out as soon as we schedule part 2.
Perfect. Thank you very much, Danielle. And thanks everybody for joining. Thank you very much. You've been very nice.
Thanks, everyone. Bye-bye.